Last week, not last week, in our last class, we started talking about stress, no? Stress. Stress, which we can denote by the letter sigma, the Greek letter sigma. So that stress is equal to force over area, right? So stress is force over area. So the unit of stress, we said that the unit is Newton per meter squared, and the dimension of this one is have the dimension of pressure, which is ml minus 1 t minus 2. Okay, so when we take stress, we further categorize into classify into two categories. One as tensile stress, and the other one is compressive stress. Okay, and so good. So tensile stress is due to tension. Now if we take a material and if we subject that material to a tension, so the stress in that we call tensile stress. If we take a material and subject to a compression, if we compress a material, so it will under compressive stress. Okay.
Yes, sir.
Good. And stress, and then we talk about strain. So strain is capital S silent. We denote from capital S silent. So strain is equals to extension over the initial length, right? So let's say we have a material, some length L. Okay, let's say I have a length L. So L is the initial length of the material, and if we subject that to a force, an external force, okay, and let's say this end of the rod is fixed to a vertical wall or something like that. Okay, and then I'm going to subject this to a force, clearly the extension. Okay, I'm applying a force F to this. Okay, so F is the external force. Okay, and now this is the extension. So strain is extension over the initial length of the material, okay, along the direction of the force applied. Okay, so here E is the extension along the direction of the applied force, and L is also the length, initial length along the direction of the applied force. Okay, so in stress we talk about tensile stress and compressive stress. Similarly, in strain also we can talk about tensile strain, where strain is due to a tension force. Now, if we consider this example, which is I drawn here, so this is, we can see that this is a tension. No? The material is experiencing a tension, so this strain is tensile strain. And if we compress this, it will have a compressive strain. Okay. Okay, so these things we discussed in our last class. Okay. Okay, and then let's the next thing we are going to talk about the variation of stress, the variation of stress versus strain. Okay. Okay, so let's put it like the variation of stress versus strain. Okay, so we are going to plot the graph here. Okay, so let us take x-axis as the strain. So strain, we take this letter epsilon, and this is stress. So in this axis, no units or dimensions, but we know the stress has a dimension of pressure, or the unit is Newton per meter squared. Okay. So now I take a material, something like this. Okay. So start from zero force. If the external force is zero, right? We know then no extension. No, is that clear?
Yes, sir.
So this graph start from the origin when this is zero, the extension or the strain will be zero, because if equals zero, E is zero, extension is zero, then strain will be zero. So, and then if I keep increasing gradually this applied force, if I keep increasing this force, we can see the variation of the graph will look like this. Okay, so we can see it is a straight line. Okay, it's a straight line variation up to some certain value, and then I'll use pencil to draw that, so we can see something like this and like this, and then here. So this is the variation of the graph. Okay, so let us mark some important points in this graph. So let's say this is the origin. Okay, I take that point O, and I consider this point. So let us take a different color, right? Okay, so here this point I take A, and this point I take B. Okay, I take this point C. Okay, and then here the maximum value of the strain I take D, and this particular point I put a cross and I take that E. Okay. Okay, so let us mark what are these points. Let's state these points. So here A, I can say A is the, now we can see this graph varies linearly up to A, right? So A is called proportionality limit. Okay, proportionality limit. Okay, and B, I can mark and state that B is the elastic limit. Okay, now I'll explain these two terms. So up to point A, the stress and strain varies linearly. Like I can state that stress is proportional to strain up to point A. Okay, up to point A, stress is proportional to strain. Okay, and then elastic limit. Now up to point B, if I take a material and stretch up to point B, it comes back to its initial position. That means the material behave the elasticity property we can see until the stress is raised to point B. If it's exceed that the value, it won't come back to the same point, same initial state or initial geometry or shape. right? So this limit is called elastic limit, right? So if you extend the material above the elastic limit, so the material won't come back to its initial state. You understand?
Yes, sir.
Okay, so and the point C is yield strength. Point C, yield strength. And point D, now point D is the ultimate, that is the maximum, ultimate tensile strength.
Point.
Ultimate tensile strength. Because you can see D is the maximum value of strain, okay? And E, point E is fracture, right? So material is breakdown. And in this graph, I'm going to draw a dotted line. Since dotted lines are not available, I use another color, maybe orange. Okay, so I want that to be from elastic limit. So somewhere from here, I draw a vertical line. Okay. Okay. So the left side of this orange line we call elastic region. Okay. So this side is elastic region, or we call that elastic deformation. Elastic deformation. Okay. And this side is plastic deformation.